Hey,
You got my Einstein shirt on today.
yeah.
Galaxy print.
Mad wavy.
Mad wavy. Mad wavy, son. But we're here for legitimately to tell you about the vocabulary.
Ooh, your favorite lecture video of the whole unit. But should we get right into it?
Sure.
All right.
This unit's about oxidation and reduction, so let's hit those up. What the heck is a reduction?
Well, there you go. There's a picture. So an oxidation is when we lose electrons.
Reduction is when you gain them.
There you go. And they have to happen together because if one atom loses an electron, it's got to be accounted for somewhere. Somebody else got to grab that thing.
So it's kind of back to bonding unit. It's an ionic transfer of electrons. So, but typically it's when an atom gains an electron. The reason why it's called reduction is because when you gain a negatively charged electron, your oxidation number goes down on the number line. It becomes more negative. So that's why it's called reduction, even though you're gaining an electron.
No rhyme or reason, I guess, other than oxygen is at play a lot of times in oxidation.
Yep.
When an atom loses an electron, the oxidation number will then increase. They're kind of equal but opposite. Ooh, your favorite.
Leo the Lion says, Gur, it's not my favorite, but I like it because it is a mnemonic device that includes the word electrons to help you understand what electrons and oxidation are. So losing electrons is oxidation, and gaining electrons is reduction. I personally use the next mnemonic device.
Yeah, and you will see it literally written on the top of my pages because I can't get it right without doing that. I highly, highly recommend you go ahead and write oil rig down because then it reminds you oxidation is losing, reduction is gaining. And of course, we are talking about nothing but electrons, this whole unit. So there you go.
That's what you're losing. Reducing agents, this is tough because reducing agents themselves are oxidized, but they are the agent of change. They allow it to happen. That's why they're called the agent. So it's the species responsible for the reduction, but it's actually being oxidized itself.
Yeah. Right.
That's it. So there's going to be an oxidizing agent, right? I think that's the next one.
Pretty much, yeah. Yep. So same picture, just in case you didn't get it the first time, different slide, right? The species responsible for the oxidation is the oxidizing agent. It's actually being reduced. So we talk about oxidation and reduction. That's one half, but there's always another piece going on. And this is almost our way to pay homage to that other piece.
Yeah. So showing the agent. So oxidation numbers, it says on our periodic table, there's a key that points to the right top square of the electron of the periodic table square is the oxidation numbers. These are the charges of ions after they have lost or gained electrons. So we're going to be playing a lot with this unit.
Yes.
And we're actually going to be instituting the concept that 0 could be an oxidation number too. And you'll see that in a future video. Yes, so we won't give it away here.
Half reaction specifically, here's 2 of them. When I look about the whole reaction, I have an oxidation and a reduction. So the half reaction is just either one of those.
Right.
There's a half reaction for oxidation, and there's a half reaction for reduction. It's written by itself, but here's the key with those. You got to get the electrons in there on the correct side.
Right.
So if I'm adding electrons, it would be on the reactant side. If I was losing electrons, it would be on the product side.
And when you combine your oxidation and your reduction half reactions, these same electrons show up on both sides.
And cancel out.
And cancel each other out. So we'll see that again in a later video.
Yeah, if they don't cancel out, we got to fix it.
Now, Voltaic cells are super important because they're running most of our electronic devices.
Yes.
This is the classical picture of what one looks like in the Regents exam with color added, of course.
Yeah, it's high-def
It's
pictures.
basically like 2 beakers, a wire with a voltmeter coming across the top, and this cool U-shaped glass tube that connects the two. So kind of memorize this image in your mind as that's a battery.
That is.
And we call those Voltaic cells.
Yes.
It spontaneously converts a chemical reaction into an electrical current or electrical energy. It's how batteries produce electricity.
You'll see that top little piece on the wire was actually what's called a voltmeter. And a lot of times in our cells that we'll see, the diagrams will be a V there.
Yeah.
It's kind of a giveaway, a little tip.
Or a switch or a light bulb.
Right. So the opposite is one with a battery. So here's the key there. An electrolytic cell has a battery in it. This is non-spontaneous. It needs a power source to make it happen. And the other thing to help pick these out is that there's just one beaker, not 2. So this is a system that is non-spontaneously converts electrical energy back into chemical energy. Of course, electricity is required to make it to go. Electrolytic, electricity needed.
Our modern cell phone batteries function both as voltaic cells and electrolytic cells. The voltaic cell, when it's not charging, you plug it in, it switches roles and decides, okay, I need to recharge myself. And that's what happens. It turns into an electrolytic cell. I know an electrode is a part of the battery. Both electrolytic cells and voltaic cells
See
have
the picture?
electrodes. There we go. It's a conductor that connects the electrolyte solution to the electrochemical cell. It kind of is the positive and negative terminals on the battery that you're familiar with from just looking at the remote batteries or whatever, but they have a special name, and it's electrode.
Yeah, they're going to be metal for us pretty much the entire time. Right?
Sometimes it could be carbon, but they are just the piece of metal that is.
There's always
the terminal.
There's an anode and a cathode.
Always.
There's a description. You see the anode's positive, cathode's negative. So there you go. The electrode where the oxidation takes place is the anode.
And the cathode is the electrode where the reduction takes place. And again, oxidation and reduction are mutual. They happen at the same. So you can't have one without the other.
Right. And then we take advantage of that in the battery, right?
Absolutely.
And there's a way to remember oxidation, reduction at the cathode and the anode. And I always learn this red cat, angry ox.
Yep. And I like this picture too because it actually shows you in that arrow above it the direction that the electrons are flowing. Right. They always flow from the anode to the cathode. If you move the anode to the left side and the cathode to the right side, the electrons will flow in the other direction. But simply put, anode is where oxidation will take place.
That's where the mnemonic comes in to help us. Same with the next one. Reduction is where the happens at the cathode. So at the cathode is where the reduction happens.
And again, reduction is gaining electrons. So you combine all four mnemonics and you kind of know how electrons are traveling in a battery circuit.
Right.
There you go.
Figure it out.
Now, a salt bridge is a critical part of a battery, a voltaic cell.
This is a good picture for one.
Not an electrolytic cell, but a voltaic cell. So you have your electrons traveling from the anode to the cathode or through the wire. That's great. But the circuit still needs to get closed. And since electrons are traveling from the anode to the cathode during their oxidation and reduction thing, ions need to offset that movement. And that's what the salt bridge does. Because remember, salts are ionic compounds. So the ions will migrate in different directions in response to the migration of the electrons, closing the circuit and making your battery work. So it enables ions to flow.
Completes the cell. Ions to flow is the key piece. Circle that. That's what you need to be able to say when you see salt bridge.
Salt bridge, ions flow.
So a little picture about spontaneous reaction relating to enthalpy and entropy. But what we need to know is that spontaneous sounds like instant.
Yep.
A reaction that proceeds all by itself. I don't need to give it any reaction. We'll be able to figure out which reactions are spontaneous and which ones aren't.
Yes. And the non-spontaneous would require some input, some force, some heat, some electricity for us, the chemists, to put into the reaction to make it happen. It's not just going to do it by itself. We have to coax it along.
Yeah, I'm not going to get up in the morning without my alarm clock.
Right.
Old school, anion, cation. So first one is anion. I see an ion gaining an electron and becoming more negative, and that's it. Old school definition back from atoms, right?
And
an atom that is gaining an electron, now a negative ion.
And we're hitting them up again because we're going to be talking about ions.
Yes, they are.
Cation is the opposite of an anion. It's an atom that has lost an electron and become positive as a result. So atoms become anions by gaining electrons, through a reduction. Atoms become cations by losing electron and oxidation. Yes. So that's how and why all these terms are starting to come back and loop back on each other and wrap around. It's a good thing that we're going to
need it to, because we're going to see metals with no oxidation number, 0, gain or lose electrons. We got to know which way the charges go. So
for sure.
Guess what?
Hold on to your shorts. This unit's mostly a review. We're going to even do some balancing equations. Gosh. Yeah. That's all, folks.
You do that good.
Bye, everybody. I can click the button to make it stop.